In this lecture, we will understand about the temperature and impurity dependence of electrical resistivity in a conductor. At a later stage, we will discuss about the temperature and impurity dependence of electrical resistivity even in a semiconductor. Let us begin with a normal conductor. While discussing the classical free electron theory, the definitions of resistivity and the resistance were made. Resistance was said to be the opposition offered by a material to the flow of electric charge. And resistivity is the resistance of a material or a conductor of unit length. Resistance is depending directly on the length of a conductor and inversely on area of cross section. That resistance is therefore equal to rho into L divided by A. Rho is the proportionality constant which is known as electrical resistivity. This indicates that resistivity is a material property, one of the important material properties. This resistivity is found to be temperature and impurity dependent. It was already told that origin of resistance is the thermal agitation, the scattering of electrons by the thermally agitated ions. When we increase the temperature of a material or a conductor, there will be the increase in thermal agitation, the lattice vibrations. These electrons during the movement from one position to another position within the material, they undergo collisions with the ions. The scattering of electrons will take place. With increasing temperature, thermal agitation also increases, therefore the obstruction also increases. This increased obstruction leads to the resistance and the resistivity. This resistivity, let us say, is a constant at a given temperature, that is room temperature. In terms of the graph, one can show that this is the resistivity at room temperature. If this is the resistivity at room temperature, when we decrease the temperature, what has to happen? The resistance or resistivity has to decrease because thermal agitations will decrease. When we go to the lower and lower temperatures, the availability of thermal energy decreases, which brings down the resistance or the resistivity. So that in this diagram, one can understand that if it is the resistivity at room temperature, when we decrease the temperature, the resistivity also decreases. And as I was mentioning, that the thermal agitation decreases with decreasing temperature, we have to expect that the resistivity should be 0 when we approach 0 degree absolute. But that does not happen. The resistivity, while it is decreasing with decreasing temperature, it becomes a non-zero value even at 0 degree Kelvin. That means even at 0 degree absolute temperature, there is some residual value of resistivity in a conductor. If the resistivity is only due to the thermal agitation, then the resistivity should be 0 at 0 degree Kelvin, but it is not happening. This leads to a conclusion that material, that conductor is not 100% pure. It has some impurity atoms. These impurity atoms will scatter the electrons. This scattering leads to this residual resistivity. So resistivity at 0 degree absolute is because of the scattering of electrons by the sides of impurity atoms. So now the concept is that the conductor is having two types of resistivities. One is temperature dependent resistivity, the other one is impurity dependent resistivity. So total resistivity is the sum of the resistivity due to impurity scattering and the resistivity due to thermal agitation or temperature dependent resistivity. This equation can be shown in this way. Rho is equal to rho naught plus rho T. Rho T represents the temperature dependent resistivity and rho is, this rho naught is the impurity scattering resistivity. So total resistivity is the sum of the two. This is called Mathiesen rule. This is all about the temperature and impurity dependence of electrical resistivity in a conductor. In the next part, we are going to understand how resistivity depends on the temperature and impurities in a semiconductor. The concept of semiconductor is not new to you. Semiconductors also have some conductivity. The conductivity is less than that of a conductor, but it is better than the conductivity of an insulator, so that it has the intermediate electrical conductivity. In a semiconductor, electrical resistivity arises not only from the electron's motion, also from the hole's motion. Therefore, electrical conductivity is the contribution from the electrons and holes in a semiconductor. But in the case of conductor, as we were discussing, the electrical conductivity is due to the free electrons. Forgotten part of this graph was the dotted line. This is in fact representing the electrical resistivity of hypothetically pure conductor. That means this is the behavior of electrical resistivity with temperature in absence of impurities. If a conductor does not have the impurities at all, then the resistivity will approach zero. That is the meaning of this dotted curve. Now I describe how temperature and impurity affect the electrical resistivity in a semiconductor. It was mentioned that the electrons and holes contribute the electrical conductivity in a semiconductor. Therefore, electrical conductivity can be expressed as the sum of sigma E plus sigma H. You know that electrical conductivity is just the reciprocal of electrical resistivity. From the classical free electron theory, we know that it is Ne square tau by m. Whereas from quantum free electron theory, we got the expression that Ne square lambda divided by m star Vf. That is the Fermi velocity. Vf is Fermi velocity, m star is effective mass, lambda is the mean free path. So the electrical conductivity is the sum of the electrical conductivity due to electrons and due to holes. This can also be written as Ne mu E plus Ne mu H, where mu is the mobility of electrons, mobility of holes. It is observed that this mobility depends inversely on temperature, but the power of temperature is 3 by 2. That means in the case of a semiconductor or a conductor, the mobility decreases with increasing temperature, or vice versa. Mobility is inversely proportional to temperature, means with decreasing temperature mobility has to increase. If the mobility increases, conductivity has to increase. But it is observed that the conductivity decreases with decreasing temperature. That means with decreasing temperature, resistivity increases in a semiconductor. Whereas in a conductor, we understood that resistivity increases with increasing temperature due to increase in thermal agitation. Or in the converse way, we say that due to decreased thermal agitation with decreasing temperature, resistivity decreases. If we think in the same way, in a semiconductor also, the resistivity has to decrease with decreasing temperature. But here, with the decreasing temperature, resistivity increases. What does it indicate? That resistivity is inversely proportional to temperature in a semiconductor. Let us understand why resistivity increases with decreasing temperature, or why resistivity increases with decreasing temperature. Let us now understand why resistivity decreases with increasing temperature or vice versa in a semiconductor. It has been shown that natural log of resistivity in a semiconductor is equal to energy gap divided by 2 kT. K is the one constant, T is temperature, and a constant, natural log of A. This is representing a straight line equation. When the resistivity is plotted, natural log of resistivity is plotted against 1 by T. This equation suggests that there should be linear relationship. That means with increasing temperature, resistivity decreases. Let us understand the reason why resistivity decreases with increasing temperature. Since I am taking the reciprocal of temperature here on x-axis to correlate with this equation, you have to understand that this is the point of low temperature and the temperature increases in this direction here on x-axis. So with increasing temperature, resistivity decreases. This is the relation. The reason is that in a semiconductor, especially in the intrinsic semiconductor, what I am speaking here is about the intrinsic semiconductor. I am considering the first case here, intrinsic semiconductor. In the intrinsic semiconductor, number of holes and number of electrons is equal. That will have equal number of electrons and holes. Therefore, this equation can be sometimes written as this is equal to, here Ne is better. Ne represents the number of electrons, Nh represents the number of holes. So you can take Ne may be common so that E can be written outside. This is the total electrical conductivity in the semiconductor. And this is the equation representing the relation between the electrical resistivity in the absolute temperature, as we have already understood that there is inverse relationship between the resistivity and the temperature. So that the temperature, increasing temperature decreases electrical resistivity. Since it is a straight line, it is easy to calculate the slope. That slope gives you this part, that is Eg by 2k. Slope is equal to Eg by 2k. So what we understand from this, if we study the electrical resistivity against the temperature, it is possible to calculate energy gap because K is constant. We can calculate the energy gap of a semiconductor by studying the electrical resistivity against the varying temperature. Now I have to tell you the reason why electrical resistivity increases with increasing temperature. We have learned that in a conductor, free electrons exist even at room temperature because of the thermal energy available in the vicinity of a conductor at room temperature is sufficient for making valence electrons free. Valence electrons become free just by observing the thermal energy. But in a semiconductor, although valence electrons exist, their energy is smaller as compared to that of the valence electrons in a conductor. Therefore, the valence electrons of semiconductors need some more energy to become free. The amount of energy that is required for a valence electron to become conduction electron or to become free electron is actually called the energy gap. Energy gap. If you supply this much of energy, then the electrons can become free and conduct electricity in a semiconductor. If the temperature increases, the thermal energy available to these electrons also increases. Therefore, the electrons will be freed from the atoms. The electrons come out of the atoms and become free electrons. Such electron creation, or you can say even ionization, increases with increasing temperature. Since we are increasing the number of free electrons by increasing the temperature, electrical conductivity increases or electrical resistivity decreases with temperature as shown in this diagram. The electrical resistivity decreases with increasing temperature due to the ionization of atoms or creation of free electrons with increasing temperature. In a conductor, at room temperature, substantially constant number of electrons are available. Therefore, if you increase the temperature due to thermal agitation and the scattering of those free electrons, resistivity increases. But here in a semiconductor, increasing temperature is creating the free electrons, which leads to the decrease in electrical resistivity. That is the reason why the electrical resistivity is inversely proportional to absolute temperature. Understand the impurity dependence of electrical resistivity in semiconductor. Because in the previous part I was talking only about the intrinsic semiconductor, wherein the temperature dependence of electrical resistivity is discussed. Now if we add some impurity to the intrinsic semiconductor, it becomes the extrinsic semiconductor. From the basics of semiconductors we have understood that. And the purpose of adding impurities to an intrinsic semiconductor is to enhance the electrical conductivity. Because basically the intrinsic semiconductors do not have good electrical conductivity. For practical applications, we need better electrical conductivity. That's why we add some impurities to these semiconductors. For example, boron will be added to silicon in order to increase its electrical conductivity. If just 10 parts per million of boron are added to the silicon, its electrical conductivity will be increased by several thousand times. That is the purpose. This is known as doping. And the electrical conductivity that arises due to impurity concentration is known as impurity conduction. So what do we understand from this? The increase in the impurity concentration decreases the electrical resistivity. We have discussed the temperature dependence of electrical resistivity in intrinsic semiconductor and impurity dependence of electrical resistivity in the extrinsic semiconductor. Now in the third part, let us look into the dependence of electrical resistivity in the same extrinsic semiconductors on temperature. Dependence of electrical resistivity on temperature. We have already understood the relation between the resistivity and temperature. So let us take the graph of natural log versus reciprocal of temperature. we have understood that in the case of an intrinsic semiconductor, ln rho versus 1 by T gives a straight line. The slope gives you the energy gap. But when we practically measure the electrical resistivity by varying the temperature, it was observed that the variation of electrical resistivity is similar to that of the intrinsic semiconductor within a temperature window starting from a lower value, but after reaching a specific temperature value, the trend changes. Assume that this is the higher temperature, about 400 or 500 degree Kelvin. Let us assume that the highest temperature that we considered for measurement is 500 degree Kelvin. Since I am taking the reciprocal of temperature, as I mentioned in the previous case also, you have to think that this is the direction of increase of temperature along x-axis. This is the lower value. Higher value will be here. Let us say it is 500 degree Kelvin. So at a given temperature, the resistivity is said to be high. That means at a low temperature. Let us say 10 degree Kelvin or 20 degree Kelvin. If you start raising the temperature from that low temperature, resistivity decreases. As happened in the case of even intrinsic semiconductor, resistivity decreases with increasing temperature. Here, in order to understand this trend, it is better if I divide this into three parts. Let us say it is part A. This region can be taken as part B, and this is the part C. Here, from for example 20 or 30 degree Kelvin to some high temperature, let us say 200 degree Kelvin typically, when we increase the temperature from such very low temperature, even from 0 degree Kelvin, if you raise the temperature to 200 degree Kelvin, resistivity decreases. But why? Reason is that in an extrinsic semiconductor, there are two types of atoms. They are the intrinsic atoms and the impurity atoms. Because we have added some dopants in order to enhance the electrical conductivity or to decrease the electrical resistivity. These impurity atoms will be ionized even at very low temperature. If we raise the temperature from 0 degree Kelvin to a typically high temperature, let us say 200 degree Kelvin, the ionization of impurity atoms will take place, which causes production of a few free electrons, which contribute to the electrical conductivity, which increases the electrical conductivity or decreases the electrical resistivity. But when the temperature reaches a specific value, about 200 degree Kelvin, that ionization in the impurity atoms will be saturated, it will be stopped. And even if you raise the temperature from 200 to some higher value, let us say 300 degree Kelvin, that kind of ionization will not take place within this temperature window between 200K and 300K. Although there are intrinsic atoms, they need higher quantity of thermal energy in order to produce the free electrons. That's the reason why at these temperatures only impurity atoms will release the electrons, whereas intrinsic atoms do not. They do not release the electrons even up to 300 degree Kelvin. So this impurity atoms stop releasing the electrons or stop producing the free electrons at 200 degree Kelvin, and if you further increase the temperature in this region, mobility will dominate. Of course, mobility was varying according to the temperature. Even in the semiconductor, we have already told that mobility is inversely proportional to T power 3 by 2. That means with increasing temperature, mobility decreases. and the decreasing mobility has to decrease the resistivity also. But in this region, the effect of the mobility was not dominant. The production of free electrons was more effective than the effect of the dependence of mobility on temperature. That's why resistivity was decreasing. But here, when a constant number of free electrons are generated, when you start raising the temperature from 200 degree Kelvin, the thermal agitation takes place, and the free electrons which were generated during this temperature will be scattered by the lattice ions, and that scattering leads to increase in electrical resistivity. Or in this region, since there is absence of production of free electrons, the free electrons which were generated here are suffering the scattering, or the mobility will decrease with further increase of temperature, which causes the resistivity to increase. As soon as the temperature reaches a higher value, typically 300 degree Kelvin, now intrinsic atoms will start releasing the electrons. If the intrinsic atoms release the free electrons or conduction electrons, again the resistivity will start falling. The conductivity will start increasing. So this is how the resistivity again starts decreasing with increasing temperature. This portion is very similar to that observed in the case of intrinsic semiconductor. That means at a higher temperature, the extrinsic semiconductor behaves as an intrinsic semiconductor in terms of the relation between the electrical resistivity and absolute temperature. This is how one can understand how electrical resistivity varies in an extrinsic semiconductor. Let me summarize. In the case of an extrinsic semiconductor, the resistivity and temperature relation is not completely linear over a long range of temperature. If we start raising the temperature from a lower value, say from 0 degree Kelvin, there will be decreasing in electrical resistivity up to a specific value of temperature. In this region, only the impurity atoms are contributing to this decreasing resistivity by releasing electrons by absorbing the thermal energy in this temperature region. When the electron activation is saturated, the produced electrons which were produced in this part will get scattered with the further increase of temperature, so that electrical resistivity increases, or in this region the decreasing mobility decreases the decreasing mobility increases the electrical resistivity. And when we increase a temperature to sufficiently high value, about to 300 degree Kelvin, the resistivity further decreases. The reason is that now intrinsic atoms will start releasing the electrons by absorbing thermal energy available in this temperature range, so that the resistivity decreases.